Oh, as we all know, the partition stretch has been widely used for FSI simulation. Depending on the number of times that the fluid and the structure solvers exchange information at each time step, the partitioned solvers can be classified into two categories. If the message is transferred only once, the method is defined as the weak coupling, like this figure shows. The corresponding algorithms are generally implicit algorithms, and the structural response in the next time step can be calculated without iterating. If the information is iteratively transferred many times in each time, the method is called the strong coupling, and the algorithms are generally implicit. OpenFOAM provides us one explicit algorithms and two implicit algorithms. Well, for those explicit single-step algorithms, there is a problem. Taking the fourth-order Runge Kutta algorithm as an example, for this 1 degree of freedom FSI system, we can reduce the order of the motion equation by introducing a state vector and then solving the structural response at the next time using the Runge Kutta algorithm as the equation shows. However, the fluid force is unknown at the next time because it is related to the structural response at the next time, which is also unknown. The traditional treatment is to freeze the fluid force in each time step. For most aeroelastic problems, the magnitude of the aerodynamic force is roughly the same as the magnitude of the inertial and the elastic force. This will lead to that the coupled time accuracy will always be the first order, no matter how high the time accuracy order of the structural solving part and the fluid solving part are. Zhang Weiwei proposed an improved Runge Kutta algorithm. We call it as IRK. They solve the unknown aerodynamic force by using an equal-step Lagrange exploration. Well, the advantages of the IRK is higher order accuracy for the loosely coupled FSI simulation, and it has a good numerical stability. And at the same time, it has some shortcomings. It can only use the B with a fixed time step. This will resulting in a lower computation efficiency. This figure shows an FSI example for the max Cron number varies with the iterations at a fixed time step. If the we can see if the max Cron number of 2.5 is allowed, then the most iterations have a smaller time step. For large variation of the structural amplitude, or for the turbulent and the non-stationary flow field, such as the downburst or the gas FSI simulation, the difference between the maximum and the minimum Cron number will be larger. And the larger it is, the lower computational efficiency is. In addition, the IRK algorithm is less versatile. It's because that estimating the max Cron number for a flow field around a complex structure is challenging. That means the time step is not easy to be determined. Sometimes it's necessary to use the max Cron number subdictionary in the contradict to control the time step. In order to solve the problem, we propose a method that is to when the time step varies in real time, such as when it is determined by the max Cron number, we use the non-equal step Lagrange exploration to approximately describe the unknown aerodynamic force. We call this method as the VTS IRK. Here is the equation, and when the time step is a fixed value, it can come back to the IRK. Okay. Besides on the 6-door rigid body motion library in the OpenFOAM, we implanted the algorithm and compiled a multi-stage vibration solver. In this solver, the first step is to initialization of the structure and the fluid at the current time. The fluid force can also be obtained. Secondly, move the time. The time step can be determined by the max Cron number or a fixed value. Then it comes to the multi-stage vibration solver. There are 4 kinds of stage. The first kind of stage is the static stage, which holds the structure in static. And this can provide a fully developed real initial fluid field. The second kind of stage is the static move stage, which is to solve the fluid-induced static displacement by applying a large structural damping, such as 0.8. Yes, and it can effectively reduce the transient dynamic effects, which is beneficial for the computational stability. And the third kind of the stage is the forced move stage. It can apply the forced vibration to the rigid body, and it can also be used to apply external excitation. The last kind of stage is the free move stage, which can solve the fluid-induced dynamic displacement by the VTS IRK in real time in the real structure parameters. User self can define the starting time and the ending time of different stages in the dynamic mesh dict. As the right figure shows, if one stage we don't need it, we can define a negative value for the starting and the ending time like this. Yes. So in this way, according to our needs and by judging the current time value, we can control whether the stage needs to be solved and the solving order of each stage. So after the multi-stage vibration solver, it comes to update the mesh and to solve the fluid field for the next time. So all process is shown in this figure. So there we use 2 cases. The first case is the flutter case of a vertical torsional Tudor-C implant. It's geometric and structural parameters are shown there. According to the 0,000 series, the theoretical solution of the flutter critical wind speed is 7.8 meters per second. To simulate this problem, we use the SSTK omega RANS model, and the fluid parameters are the airs parameters. The computational domain and the mesh are shown here. We use a 2D simulation, so the front and the back face are empty. We divide the mesh into structured mesh near the body wall and unstructured mesh away from the body wall. The boundary conditions are also shown in this table, and the wall functions are used. Discretization schemes are also shown in this table. The discrete accuracy is second order, and the limiter is used to ensure the stability. I also put the solution string on here. 2 N characters and 2 N outer characters are used for the pimple form. Yes, here is the result. Firstly, fixed time value, time step is used. It can be found that when the wind velocity equals 8 meters per second, the displacement gradually decreases with the time after the excitation. The middle figure shows the max Cron number varies with the time. The max Cron number also decreases with time. Also decrease with the time after the excitation. Yes, the total execution time is around 45,000 seconds. When the wind velocity equals 8.1 meters per second, we can find that the displacement amplitude gradually increase with the time, which means that the aerodynamic instability occurs. This simulated the simulated critical wind speed is 3.8% higher than the theoretical value, which may be due to the geometrical shape is not an ideal simplant, and the turbulent model may also cause the error. The max Cron number increased due to the increase of the displacement's amplitude. The total accuracy time is almost the same. Both the two cases max Cron number is around 3. So this time we use the max Cron number of 3 to control the time step. We can find that the same results can be obtained by the two methods. Meanwhile, the iterations can be reduced by 25% and 22% respectively. And the total overall equivalent calculation speed is increased by 38% and 33%. Under the variation mean velocity, we can obtain the variation time history and extract the frequency and the total damping ratio. It can be also found that the simulation results agree well with the theoretical solutions. The VTSI RK has the same accuracy with IRK. Under the condition of the almost the same max Cron number between the IRK and the VTSI RK, the table shows the reduced iterations and the raised speeds. We can find that when the wind velocity is equal to 6 meters per second, the reduced iteration reached 44%. 44%, which is the most among these cases. The graph below shows the time history, max Cron number, and the variable time step. In this condition, in fact, as we can show the middle figure that when the wind velocity increased from 0 to 6, both the vertical and the torsional total damping ratios increase. Therefore, the amplitude decays the most at this condition, and the same for the max Cron number. So when the wind speed increases further, the total torsional damping ratio begins to decrease until it reaches 0, and the flutter instability occurs. At this time, the simplant exhibit limited circle oscillation with a constant amplitude, so the number of the reduced iterations is relatively small. The law of the raised speed is basically the same. So there are some cases are not calculated on the same hardware condition. So the execution time is not shown. Okay, another case is the vortex-induced vibration of a vertical lateral two-valve cylinder. The parameters is shown here, and the dimensionless mass is 10, diminished velocity is 5, and the Reynolds number is 100. To simulate this problem, we use the laminar simulation, and the fluid parameters are shown above. The computational domain and the mesh are shown here. We also use the 2D simulations. All are the structure and mass. The boundary conditions and the discretization schemes are much simpler. The accuracy is also second order, and no limiter is used. For this problem, the outer characters is set as 4. Okay, after the static stage, the cylinder vibration from the rest and the simulated vertical amplitude agree with the reference value, but the lateral amplitude are somewhat different, which need to be further studied. This table shows the iterations and the execution time at a different time range. We can find that for the increasing amplitude vibration, the VTSI RK's effects are more obvious. It can reduce the iterations about 25%. This slide shows more clearly shows the usefulness of the multi-stage vibration solver. This figure indicates that the cylinder under this fluid field velocity, it has only one stable limited circle oscillation amplitude. The final is the conclusion. Firstly, VTSI-RK has the same computational accuracy as IRK under the same max Cron number. It can reduce the iterations and raise the calculation speed. And VTSI-RK is a versatile solver that can be used in both fixed time and variable time step, making it highly suitable for use with OpenFOAM. Secondly, VTSI-RK can save more computation resource for the FSI problem, which with the large quantum variations such as the time varying structure amplitude and the time varying flow velocity. In addition, for large-scale 3D simulations, the advantages will be more prominent. Thirdly, is that the multi-stage vibration is convenient for conducting the FSI studies. That's all my presentation. Thank you for your listening.
Okay, a very interesting talk. So, any questions to the presentation? Okay, I have a quick question. So if we use the variable time step in the RK algorithm, maybe the time step will be small or large. So how's the stability of the scan compared to the classic RK scan?
I think the stability is the same, and I have tried some different schemes that such as the multi-step algorithms, and I change it to the variable time step too, and the stability and the research show that the Runge Kutta algorithm, neither the fixed time step or the variable time step shows a good stability. So I prefer this algorithm for the variable time step simulation.